For this series in Spacecraft Guide, we are going to focus on the Space Shuttle. We're going to concentrate on the flight instruments to teach you how the astronauts flew the Space Shuttle in flight and in orbit. In this episode of Spacecraft Guide, we are going to start focusing now on the primary flight display and the instruments inside of it. And specifically, we are going to focus on this part of the ADI, which is the attitude ball. When you click on this area right around here, it takes you to the actual attitude ball. Now, I to scrape one of these, find one with all of the markings. This is just to show you exactly what is on the ball. It looks like what you would see in an airplane, but there are some subtle differences that can really throw you off, because it threw me off the first time I looked at it as an airline pilot. And first thing, okay, so what we have here is the artificial horizon. Now, this is the difference between the ground, or what I consider the ground, and the air, but really it's negative numbers and positive numbers, okay? But in a sense too, that isn't true also, because it's based on a 360-degree scale. So you see here is 0. Here is 30 degrees, 30 degrees. I took that to mean 30 degrees pitch up, but it's not. So you have 60 degrees up here. You come back around to the bottom here, you have 300, 330, 300, and 0, which is 360 degrees. So what that's telling you here is your relationship in a 360-degree turn. It doesn't have to do with your relationship to the horizon. This is just 0. And then we also have the belly band right here. Now, this is the center for what most people would think of as pitch, but it's not pitch. It's moving either way. Again, going to the right here, you'll see, this is yaw. So this is considered 365 degrees, or 330 degrees, 30 degrees of yaw. And then we see 60 degrees of yaw as you go to the right. Coming around from the left, you see 300 and 330. That is all based on this belly band here for yaw. And again, this is not pitch. This is the way the airplane is, or the spacecraft is turned. So it's the way your nose is pointed. So on this platform, you'd be on, say, 0 pitch, and now you want to turn the nose of the airplane 30 degrees, and that would be on the compass to the right. And then you wanted to come back to 0, and then you would want to move the nose of the spacecraft 330 degrees to the left. So this isn't, like I said, in an aircraft, this would be 30 degrees either side, and this would be 30 degrees up and down. But here we only have pitch and we have yaw. Okay? And now it's now we're going to go a little bit deeper for our Patreon subscribers, and we are going to go into the schematics. Now this is for our free and paying subscribers. So what are you waiting for? It's free to go into to see how this ball is moved. Okay, so when you're a subscriber to my Patreon page and you click on schematics, it will take you to the old version. Now this is from, you can see this is from the lunar module of Apollo, and this is the best explanation I can get of how this ball works. Okay, so you would think, oh, this is the attitude ball, but it's not. This is the reference that they use, and as you see, they call this the stable member, and there's 3 gyros in them, and they're all 90 degrees of each other, and that's to try to remove the precession that the ball or the movement as friction builds up. This tends to turn on the platform, tends to turn a little bit on it, and if you have 3 gyros like this lined up, then you won't have as much of a precession, but you're always going to have a little bit, and that's why you're always referencing, which we will go to later to explain how that is for our paying subscribers. And if you look in here, we have, they call it gimbals. All right, so on this stable member that they have in the spacecraft, so in this case the shuttle, or that could be on the any of the Artemis spacecraft, SpaceX, the Boeing Starliner, and Orion, they have this stable platform, and then they have the gimbals. And at the gimbals, you see we have one for the X, the Y, and the Z-axis. Z-axis right there. What they're going to do is they're going to measure the distances, the measurements right here, the angle of the gimbals. Now these rings are called gimbals, and they are measuring this gimbal right here, as you can see, and they call it with a torque motor duplex ball bearing slip ring. So it is moving on this duplex right here, and they're measuring that instrument, and then that goes back to the ball, and it changes the ball to mimic what is in the stable platform. But then there's more to it, because the platform here is to mimic what you want in space. And now for our paying subscribers, we're going to go a little bit deeper into that, into how this is referenced. And for paying subscribers, which again is $4 a month, that's just like a cup of coffee. Come join us on my Patreon page for $4, and I'll tell you how and why they reference that. So if you're a paying member and subscriber, and we click on General, we're going to go to the Guidance, Navigation, and Control. If we come down to this right here, it says the actual attitude is derived from inertial measurement unit angles. Aerosurface position is provided feedback to the transducers in the aerosurface servo amps. Body rates are sensed by the gyro assemblies, and accelerations are sensed by accelerator assemblies. So right here we see inertial measurement unit angles. This is that IMU that we just saw. Now, what that is going to do is be our stable platform. But this stable platform on this ball is basically in 2 things. One they have is, they call it, if we go back one more, right up here, LVLH. And I have been messing that up a little bit. This stands for local, vertical, local horizon. That is the term, local, vertical, local horizon. And what that means is in reference to the large mass that it's orbiting, called Earth. So this all has to do with the local, vertical, and the horizon, the vertical and the horizon in relation to Earth. And again, you can see Earth is right here, this black spot, and that's just the reference. Now, with spacecraft, this could be the moon if it was Artemis going to the moon. So this is what the platform is set to. So the platform, it might be cockeyed some way, but they took the star sign. What they do is they take the star signs, the star maps, and they plot out where they are, and then they put that in there. But then there's not only local vertical, local horizon, there's another one called inertial reference. And when we look into that, it tells us that the attitude ball, is set up for the useful reference. So inertial means useful reference. So what is a useful reference? Well, say the thing that you're docking with. They get the information from the International Space Station, and they put that information into here, and now you're not navigating according to the LVLH, local vertical local horizon, or the large body called Earth, or the large body called the Moon. You're referencing whatever you want to dock with. So it could be the International Space Station, it could be the object orbiting the moon that you're going to dock with before you go down to the surface of the moon. That's what it will be. And up here will be inertial. So that's really what this ball is. It just has reference to what you want to use because there's no up and down in space. That's just reference to what you are. But we're so used to gravity that we need an up and down because our minds can't compute no up and down. And that really gets us confused in our mind. And that's when we start getting sick and space sick. So there you have it. That's all for this week. I want to thank you again for supporting me. Please tell others to help support me on this. Got a little bit more money this year, so we started going into more things on the space shuttle. And also the great thing about doing the space shuttle and its upgrade with the CRTs, the cathode ray tubes, is that's the same kind of reference that you see used in spacecraft, so the current spacecraft. So you're kind of getting more bang for the buck on the historic one here because we're giving you insight to what the other spacecraft that are going to the moon and Mars will look like. And again, I thank you.